So Chris, thank you for joining me on this video.
My pleasure.
It's we met before, but we met in CITES.
Yes.
And on that conference, you said something I've never thought about before, and
Okay.
it was that when you tried to figure out the distribution of a response, it's important to take the factors into account.
Yes, it's essential.
Why? Why is that important?
Well, I can give an example very easily. So I go to DOE, custom design, and I'm going to add a single categorical factor with 2 levels. And to make it relatively easy for us to see the distribution, I'm going to increase the number of runs to 64. So that's far more than we would need typically.
Far more.
Far more. But
that's not the intent.
Example. We just want to make it obvious and clear.
Yeah.
I'm going to make design, and then I'm going to create a data table simulating responses.
All right.
And I'm going to change the coefficient for x1 to 2.
Can I try and put some words on that? You can correct me if I'm wrong.
Go for it.
So when we set that to 2, and it's a 2-level factor, that would mean that the difference between the two would get to 4, because if the 0 was the mean of that, the high level of, let's say L1 is the positive one, that would be +2, and L2 would then be like -2.
That's correct.
Okay.
That's right.
But that means that when the error I can see is 1, we would definitely be able to still these apart.
Yes. Yes.
Okay.
So yeah, we should
Especially at 64.
Especially with 64, we should see 2 bunches of groupings of observations. One over around -2 and another one around +2. So I'm going to click apply, and now Y simulated has been updated.
All right.
And I'm going to take a look at this in the distribution platform. And we can just click the column we want and then go straight to OK. So this little trick. So I'm going to try fit all. And what we see is that the normal 2 mixture distribution has come up as the best, followed by the Shash, which is a very flexible distribution, and then the normal 3 mixture, and then the normal distribution. So the normal 2 mixture here is correct, but we would never use that as like the error distribution once we're trying to include variables. So we're separating out those two, the concept of the distribution of the response and the factors that are driving changes in the mean of that response. This is totally correct, but if we're going to use this as the starting point for a regression analysis, we're never going to use the normal 2 mixture distribution as our error distribution. The correct distribution is that the correct model rather, is that there are 2 groups of observations, and one at the value at the level 1 value, and they have a mean of around -2 or 2. And then the other at the other level, they have a mean of -2.
There's a few things here I'm thinking about. If I was looking at let's say I'm in quality, I'm only looking at a single response and how it's performing as a function of time, and I want to see the distribution. I could easily make the mistake that we're making here. Like, let's say that I'm pooling 2 different kind of raw material, and I don't know anything about the process. I'm just looking at it. I would say, well, it has a 2 mixture normal. So if I weren't doing the next step, I would never figure out like why is it
the 2 distribution here. In that case, if you have 2 different like suppliers and they have different input distributions, then in your production measurements you would probably see 2 separate distributions. If you want to take into account supplier, then you would want to like go to GenReg and do your regression modeling, including that as an effect. If you didn't want to do that and you wanted to make an overall statement about your quality or capability analysis, ignoring suppliers, so that might be the view that your customer has, then you might want to use that 2 mixture, because that's what they're going to see at the end.
For them, that's the true distribution.
That is the true distribution. So,
but for regression
purposes, you would not start here in this way.
No. So what would be the next step?
Well, so here we would backup because this is sort of a dead end if we're going to take into consideration the factors. The right next step in this case would be to go to the Analyze menu, go to Fit Model, and then we'll load up Y simulated as our response instead of Y. And I'm going to load up X1 as my input, so it's already there. We're going to use genreg because it's, so we'll start off with the normal distribution. And we're going to apply a variable selection to this to determine basically, is this factor important or not? And it is. Now we can ask about other distributions.
Model launch.
Yeah, model launch, sorry.
In these kind of videos, I'm the one that points to stuff. It's mine.
I'm sorry?
No, I'm just saying I'm the one that points. Now you're driving, so I'll be the point.
Okay, yeah, cool, yeah, great. Here we've got positive and negative values, so we don't have a choice,
right.
A lot of choices about the distribution. We can try the Cauchy, which is a robust distribution. Here it's actually picking this up correctly.
So, but basically, any kind of distribution our response would have, if we're loading it into the generic platform, and we're loading it simultaneously with the factors, we could be screening out different response distributions
at the same time.
That's
right.
So that's actually like both very strong and very simple.
Yes, we've made it. I think we've made this easier than anybody else has.
Yeah, and we can easily then compare those two here in this model comparison window where we have the AIC. And what I've also learned is that while p-values across models are not really comparable,
they're not.
AIC is.
It is.
So that's why we're using AIC. Like, why do we use something that's more... So the idea is that AIC will always, if it's lower, it's better.
If it's lower, it's better.
Yeah, it's like p-value is not, like you want to have it as low as possible. But
that's what that depends on the question you're trying to ask.
In comparison, ideas.
In comparison, yes. So the p-values are, they require you to actually believe the model that you're using, right? And they also implicitly assume that the model, that the question that you're asking with the p-value was one of the questions you were intending to ask in advance.
Right.
And so once you've used a variable selection procedure to add variables or remove variables from the model, you never had any intention of asking the question. If you had 10 factors and the variable selection algorithm chose 5 of them and you're looking at the p-values of those, you're not looking at those as if you had like known in advance that those were the 5 factors you're going to be working with. But those p-values assume that. And if you change the variable and if you change the model and add or remove terms and the p-values change in one way or another, there's no reason to compare those p-values in any way. This is a silent assumption that people make very easily, but there's no validity to it whatsoever.
Okay. But AIC would be robust.
So the AIC allows you to compare models that have different distributions, have completely different factors. Selection procedures.
Yeah.
You can have correlation structures in there also. You can as long as you're working with a probability model and you're using maximum likelihood to estimate the parameters, then any model that you fit that way will give you an AIC or an AICC that is comparable to any other combination of model, distribution, and correlation structure that you fit anywhere else. So everything is completely comparable.
Yeah, that is very powerful. But thanks for that explanation, Chris.
Yeah, my pleasure.
Yeah, that helped a lot.
Great. Well, thank you. Yeah, this is fun.
Thanks. Thank you for watching. Chris is going to be doing an extended talk on this topic. If you have any questions you would want me to try and go over with Chris on some of the more advanced features in JMP Pro, either the functional data explorer or the generalized regression platform, let me know in the comments. But give it a like if you liked it, subscribe if you want more content like this, and catch you in the next one. Bye.